What if the universe wasn't built on order but on chaos? Picture a reality where particles crash randomly, forces pull in all directions without rhyme or reason, and the very fabric of existence shifts like sand in a storm. It would be a cosmos without structure, without beauty, without life as we know it. Yet, that's not the universe we live in. Ours is a universe of breathtaking symmetry, where hidden patterns weave through the fundamental forces, shaping everything from the tiniest quantum interactions to the grandest galactic designs. This symmetry isn't just a happy accident, it's the silent architect of reality itself, a cosmic blueprint that hints at something far deeper than chance. Think about the last time you marveled at a snowflake's intricate design or the perfect spiral of a galaxy. These aren't just pretty coincidences, they're glimpses into a universal language of balance, a language written into the laws of physics. Symmetry is the thread that ties the cosmos together, from the way particles mirror each other in perfect harmony to the way gravity sculpts the universe into elegant, predictable shapes. Even the equations that describe our reality, those complex strings of numbers and symbols, hold symmetry at their core, as if the universe itself is solving a puzzle with infinite precision. But why does symmetry hold such power? What is it about this hidden order that makes it so essential to existence? The answers lie in the very forces that govern our universe, forces that seem to follow an unspoken rule of balance. From the electromagnetic dance of charged particles to the gravitational embrace of stars, symmetry isn't just a feature, it's the foundation. And as we peel back the layers of this cosmic mystery, we'll discover something extraordinary. Symmetry might not just describe the universe, it might explain why the universe exists at all. So let's begin this journey, tracing the invisible lines of order that shape everything we see, everything we are, and everything that ever will be. Take a moment to look at your own hands, two mirror images, nearly identical yet reversed. This simple symmetry isn't just a quirk of biology, it's a whisper of something far grander. The same principle that shapes your body also sculpts galaxies, arranges atoms, and even dictates how light travels through space. Symmetry is nature's favorite blueprint, appearing everywhere from the microscopic dance of electrons to the vast, swirling arms of the Milky Way. Consider the snowflake, a masterpiece of hexagonal perfection, no two ever exactly alike yet all bound by the same geometric rules. Or the Nautilus shell, its spiral growing in flawless proportion, each chamber a mathematical echo of the last. These aren't just pretty accidents, they're clues to a deeper truth. The universe doesn't just tolerate symmetry, it demands it. Even the forces that hold reality together, like electromagnetism and gravity, obey symmetrical laws so precise they can be written as elegant equations. But here's the real mystery. Why does symmetry hold such power? One compelling idea is efficiency. Symmetry minimizes wasted energy, creating structures and systems that are stable, predictable, and resilient. A butterfly's wings aren't symmetrical just for beauty. Their balance allows for precise, energy-efficient flight. In the quantum realm, particles and antiparticles mirror each other, a symmetry so fundamental that if it were violated, matter itself might not exist. And then there's the cosmos. When astronomers map the large-scale structure of the universe, they don't find chaos, they find filaments and voids arranged in vast, repeating patterns, like foam on the surface of an endless ocean. This cosmic symmetry suggests that the same forces shaping a single atom also sculpt the universe on the grandest scales. It's as if nature has a playbook, and every chapter, from the smallest quark to the largest supercluster, follows the same golden rule: balance. So the next time you notice symmetry in the world around you, remember, you're not just seeing a pleasing pattern, you're glimpsing the hidden code of reality itself, a language written into the fabric of space and time. And the more we decode it, the closer we get to answering one of science's greatest questions. Why does the universe play by these rules at all? If mathematics is the language of the universe, then symmetry is its grammar, the invisible structure that gives meaning to every equation. This profound relationship was crystallized in the early 20th century by mathematician Emmy Noether, whose revolutionary theorem proved that every symmetry in nature hides a conservation law. Picture a spinning ice skater pulling their arms in their rotation, speeds up while their angular momentum stays perfectly constant. That unchanging quantity isn't accidental, it's guaranteed by the symmetry of rotational motion. Noether showed this principle scales to the cosmos itself. The fact that physical laws don't change from moment to moment times symmetry gives us the conservation of energy. The uniformity of space translational symmetry protects momentum. Even electric charge persists unchanged because of a deeper symmetry woven into quantum fields. These aren't abstract curiosities, they're the scaffolding of reality. Take gauge symmetry, the mathematical principle ensuring that particles like electrons behave consistently whether observed in Tokyo or on Mars. This cosmic democracy, the idea that fundamental interactions shouldn't depend on arbitrary reference frames, forced physicists to predict the existence of force-carrying particles before discovering them. The photon, gluon, and W and Z bosons all emerged from equations demanding symmetry, like invisible guests RSVPing to nature's most elegant party. When Peter Higgs and colleagues proposed a mechanism to explain why particles have mass, their solution didn't break symmetry, it hid it, like a needle threading through the fabric of spacetime itself. The Standard Model, that triumphant catalogue of particles and forces, resembles a symphony where each instrument's part must harmonize with the whole. Quarks, leptons, and bosons aren't solo performers, they're interconnected through symmetries so exact that altering one interaction would unravel the entire composition. Imagine a cosmic game of Jenga where removing any symmetry block would collapse the tower of physical law. This delicate balance explains why protons last billions of times longer than their unstable cousins, and why sunlight reaches Earth with unfailing regularity despite the quantum chaos brewing inside stars. Yet for all its power, symmetry isn't absolute. The universe plays with broken symmetries too, like a sculptor deliberately chipping marble to create something new. When the early cosmos cooled, symmetries froze into distinct forces, electromagnetism peeling away from the weak nuclear force, like twin siblings taking different paths. These fractures gifted reality its richness. Without them, quarks might never have clustered into protons, and chemistry's intricate dance would lack its players. Even the arrow of time may owe its existence to symmetry-breaking, that moment when the primordial cosmos chose structure over uniformity. This interplay of perfect order and creative imperfection raises a tantalizing question. Is symmetry the universe's default setting, or is it something deeper, a prerequisite for existence itself? As we peer through telescopes and particle colliders, we're not just mapping the cosmos, we're deciphering a love letter written in the language of balance, where every equation whispers the same profound truth. Without symmetry, there would be no universe to admire, and no one left to admire it. Imagine the Big Bang not as a chaotic explosion, but as a flawless crystal, a moment when every force, every particle, every shred of energy existed in perfect, undifferentiated harmony. In those first searing fractions of a second, the universe wasn't just symmetrical, it was symmetry itself, a singularity where all physical laws blended into one unified song. Then, like a cosmic clockwork unwinding, that pristine symmetry began to fracture, with each passing instant as the newborn universe expanded and cooled. Hidden layers of structure emerged, much like a single beam of white light splitting into a rainbow. What caused this grand unraveling? Think of it like water freezing into ice. At high temperatures, water molecules move freely, their arrangement fluid and symmetrical. But as temperatures drop, that symmetry breaks, the molecules lock into rigid patterns, creating ice's crystalline structure. The early universe underwent similar phase transitions. As it cooled, the single unified force splintered into the four fundamental forces we know today: gravity, electromagnetism, and the strong and weak nuclear forces. Each fracture was a creative act, forging the diversity that makes our universe so rich and complex. The most famous of these symmetry-breaking events involves the Higgs field. Picture an endless, invisible ocean filling all of space. In the early universe's extreme heat, this ocean was perfectly calm, a symmetrical state where particles raced through it weightlessly, like skimmers on a still pond. But as temperatures dropped, the Higgs field froze into a new state, like ice forming on that pond's surface. Suddenly, particles moving through it encountered resistance, what we experience as mass. Some, like photons, slipped through untouched, remaining massless. Others, like electrons and quarks, grew heavy, their properties shaped by this broken symmetry. Without this cosmic tipping point, atoms could never have formed, and the universe would be a sea of featureless energy. These transitions weren't accidents, they were inevitabilities written into the fabric of reality. The mathematics behind them is so precise that physicists could predict the existence of particles like the Higgs boson decades before detecting them. It's as if the universe left breadcrumbs of symmetry in its equations, guiding us to uncover its deepest secrets. And every time we peer back toward the Big Bang, we find the same startling truth. What looks like chaos is really order in disguise, a masterpiece of balance that set the stage for everything from stars to cells to conscious minds. Yet here's the beautiful paradox: symmetry-breaking didn't destroy the universe's underlying order. It transformed it. Like a seed splitting open to release a tree, those primordial fractures created the conditions for complexity to flourish. The very asymmetries we see today, the dominance of matter over antimatter, the arrow of time, even the irregular distribution of galaxies, are echoes of that initial perfection, reminders that symmetry isn't just a static rule. It's a dynamic force, a cosmic choreography that balances creation and destruction, unity and diversity in every atom and every galaxy. And as we trace its fingerprints across the cosmos, we're not just studying the universe's past, we're uncovering the principles that continue to shape its future. Gravity doesn't just pull apples from trees, it bends the very stage upon which the universe performs. Einstein's revelation that space-time curves around massive objects wasn't just a breakthrough in physics, it was a testament to symmetry in action. The equivalence principle, the idea that gravity's tug feels indistinguishable from acceleration, is symmetry wearing a disguise. Whether you're standing on Earth's surface or hurtling through space in a rocket, the laws of physics remain impeccably consistent, a cosmic democracy where no frame of reference holds privilege over another. This isn't just poetic, it's predictive. When astronomers observed starlight bending around the sun during a solar eclipse, they weren't just validating relativity, they were catching symmetry red-handed, warping the fabric of reality itself. Then there's electromagnetism, the force behind every spark and sunset. Its symmetry, known as gauge invariance, is like a master artist ensuring a painting looks identical whether viewed under daylight or candlelight. Change the lighting of an electromagnetic system, adjust its potential energy, say, and the underlying physics stays untouched. This symmetry doesn't just explain why your compass points north, it demanded the existence of the photon long before we detected it. The equations literally couldn't balance without it, but the nuclear forces take symmetry to even stranger depths. The strong force, which glues quarks together inside protons, operates under a symmetry so precise it's described by a mathematical structure called SU3. Imagine a kaleidoscope with 8 mirrors reflecting quarks in endless permutations, each turn preserving the rules of their interactions. Meanwhile, the weak force responsible for radioactive decay reveals symmetry's creative power when broken. The fact that it treats matter and antimatter slightly differently, a tiny asymmetry, might explain why we live in a universe filled with stars and planets instead of empty radiation. These patterns aren't just mathematical decorations, they're cosmic necessities. Without them, particles wouldn't bind, stars wouldn't shine, and the delicate balance permitting chemistry and life would collapse. When symmetries break, they don't vanish, they transform. Like a frozen river cracking into intricate ice patterns, each fracture encodes information about the universe's infancy. The Higgs field symmetry breaking left us mass. The separation of the nuclear forces forged atomic diversity. Even the slight asymmetry between matter and antimatter might be why you exist to ponder these questions. So when we ask if these patterns hint at a grand design, we're not invoking mysticism, we're following the evidence. The universe doesn't just contain symmetry, it's saturated with it, as if every law, every particle, is a note in a composition too coherent to be accidental. Whether this points to a deeper layer of reality, a multiverse, or simply nature's relentless efficiency, one thing is clear: symmetry isn't just how the universe works. It might be why the universe works at all. The universe has a curious habit of breaking its own rules, or at least bending them in ways we don't fully understand. Take antimatter, the mirror image of ordinary matter, with particles identical in mass but opposite in charge. If symmetry held absolute sway, the Big Bang should have crafted matter and antimatter in perfect balance, leaving them to annihilate each other in a burst of pure energy. Yet here we are, surrounded by galaxies, planets, and coffee mugs made of matter, with antimatter vanishingly rare. This cosmic imbalance, called CP violation, is like finding a single flipped tile in an otherwise flawless mosaic, a tiny crack in the universe's symmetrical facade. The mystery deepens when you consider just how precise this imbalance had to be. For every billion antimatter particles created in the early universe, there were roughly 1,000,000,001 matter particles. That razor-thin margin, just one extra particle in a billion, was enough to tip the scales, leaving behind the raw material for everything we see today. Without that slight asymmetry, the universe would be an empty sea of radiation, devoid of stars, planets, or life. So why did symmetry falter here, of all places? Physicists have uncovered clues in the behavior of exotic particles like kaons and B mesons, which decay slightly differently than their antimatter counterparts. It's as if the universe has a subtle bias, a preference for matter written into the fine print of quantum interactions. Some theories suggest hidden symmetries, one so profound they're invisible to our current experiments, might be pulling the strings. Others speculate about undiscovered particles or forces that tip the balance in those first critical moments. The answer might even lie in the neutrino, the ghostly particle that barely interacts with matter at all. If neutrinos are their own antiparticles, as some experiments hint, they could have triggered a chain reaction favoring matter's survival. But perhaps the most tantalizing idea is that this asymmetry isn't a bug, it's a feature. Just as broken symmetry in the Higgs field gave particles mass, the matter-antimatter imbalance might be another creative fracture, a necessary twist in the cosmic recipe. Without it, the universe would lack structure, diversity, even the possibility of observers like us. In that sense, CP violation isn't just a puzzle to solve. It's a reminder that symmetry's greatest power might lie not in perfection, but in its carefully calibrated imperfections. And as we probe deeper into this enigma, we're not just chasing particles, we're unraveling the very conditions that made our existence possible. Supersymmetry whispers an audacious idea. What if every particle we know has a hidden twin, a mirror image waiting to be discovered? This elegant theory, known as SUSY, suggests that the quantum zoo is twice as crowded as we imagined, with every fermion the building blocks of matter paired with a boson the force carriers, and vice versa. Imagine electrons shadowed by hypothetical selectrons, or photons with photino counterparts, a cosmic dance of partners we've yet to spot. At first glance, this might sound like theoretical excess, but SUSY isn't just whimsy. It could solve two of physics' greatest mysteries in one stroke. First, consider the hierarchy problem, the baffling gap between the featherweight scale of gravity and the titanic strength of other forces. Gravity is weaker than electromagnetism by a factor of 1 followed by 36 zeros. That's like comparing a single grain of sand to the entire Milky Way. SUSY offers a way out. If every known particle has a superpartner, their interactions could cancel out quantum fluctuations that otherwise make gravity appear absurdly feeble. It's like discovering that two identical but opposing ocean currents have been masking the true depth of the sea beneath them. Then there's dark matter, the invisible glue holding galaxies together. None of the particles in the standard model fit the bill, but SUSY's lightest superpartner, often dubbed the neutralino, could be the perfect candidate. Stable, massive, and barely interacting with ordinary matter, it's as if the universe left breadcrumbs in the form of missing symmetry, guiding us toward the invisible 85% of its mass. Yet for all its promise, SUSY remains elusive. Particle colliders like the Large Hadron Collider have hunted for superpartners at energies where they should have appeared, only to find empty corridors in the data. Some theorists argue we might need even higher energies, or that superparticles are hiding in plain sight, camouflaged by properties we don't yet understand. Others suggest SUSY might manifest in ways we haven't imagined, like extra dimensions or broken symmetries at cosmic scales. The stakes couldn't be higher. If SUSY is real, it would mean the symmetries we've observed so far are just the surface of a far deeper order, a shadow universe of particles waiting to rewrite the rules. And if it's not, that absence would be just as profound, forcing us to confront the unsettling possibility that nature's elegance might not align with our human love for balance. Either way, the hunt for supersymmetry isn't just about particles. It's about whether the universe's grand design includes partners we've yet to meet, or if its symmetry hides in stranger, subtler forms we're only beginning to trace. The universe's opening act wasn't just fast, it was a masterclass in controlled chaos, where symmetry played both architect and demolition expert. Picture the cosmos in its first trillionth of a second, smaller than a proton yet hotter than a supernova. Under these extreme conditions, a mysterious field, call it the inflaton, held dominion, its perfect symmetry driving space to expand exponentially faster than light itself. This wasn't expansion as we know it today, with galaxies drifting apart like leaves on a pond. Inflation was space-time itself being stretched, ironed flat until any primordial wrinkles vanished, leaving behind a universe so uniform that temperatures vary by less than 1 part in 100,000 across billions of light years. What's astonishing isn't just the speed, but how quantum fluctuations, tiny ripples in the inflattened field, got frozen into the fabric of reality during this stretching. These microscopic imperfections, born from Heisenberg's uncertainty principle, became the seeds for all cosmic structure. The symmetry of the inflattened field meant these fluctuations weren't random noise. They followed precise statistical patterns called scale invariance, where clusters of matter look similar whether you're examining a cube of space 1,000,000 light-years wide or 1,000,000,000. This signature, imprinted in the cosmic microwave background like a fingerprint, tells us inflation didn't erase symmetry, it translated it upward, transforming quantum fuzz into galactic superclusters while preserving mathematical harmony across scales. The aftermath reveals symmetry's clever trick. As inflation ended, the inflattened field decayed in a process called reheating, transferring its energy to create the hot soup of quarks and gluons we call the Big Bang's afterglow. Crucially, this transition maintained certain symmetries while breaking others, like a spinning top that loses stability but conserves angular momentum. The result, a universe where the large-scale structure appears statistically identical in all directions isotropy, yet contains enough localized asymmetry to form stars and planets. It's this delicate interplay global symmetry permitting local variety that makes our cosmos both comprehensible and complex. Some theorists go further, suggesting inflation symmetry might be a clue to spacetime's quantum origins. Just as crystalline solids emerge from symmetric atomic lattices, perhaps space-time itself condensed from more fundamental building blocks obeying deeper symmetries we've yet to uncover. If true, then every galaxy, every black hole, even the void between stars might be secondary patterns emerging from primary symmetries as profound as those governing subatomic particles. The echoes of this idea appear in holographic principal theories, where our three-dimensional reality could be a projection of information encoded on a two-dimensional surface, a cosmic symmetry so radical it redefines what real means. So when we map the distribution of galaxies or measure the microwave background's faint anisotropies, we're not just doing astronomy, we're reverse engineering the universe's opening gambit, tracing how perfect symmetry birthed imperfect beauty. And with each new observation, from gravitational wave detectors to next-generation space telescopes, we get closer to answering whether symmetry was the spark that ignited existence, or merely the first stroke in a far grander design still unfolding around us. String theory doesn't just tweak our understanding of reality, it rewrites the entire score. Imagine every particle in the universe isn't a point but a tiny, vibrating string, its oscillations composing the cosmic symphony we call matter and energy. The pitch of these vibrations, whether they hum low like a bass note or sing high like a violin, determines whether we're looking at an electron, a quark, or even a photon. But here's the twist: these strings don't dance in the 3 dimensions we know. They vibrate in 10, maybe 11, hidden dimensions curled into shapes so intricate they make snowflakes look simple. These geometric masterpieces, known as Calabi-Yau manifolds, are symmetry incarnate, their folds and creases echoing mathematical harmonies so precise they could only exist in the mind of the cosmos itself. What's staggering isn't just the elegance, it's the ambition. String theory doesn't merely add dimensions for fun. It uses their symmetrical geometry to unify gravity with quantum mechanics, 2 frameworks that have resisted reconciliation for a century. Picture a grand piano where every key plays a different force: electromagnetism, the strong and weak nuclear forces, gravity. In our current model, some keys are out of tune, their notes clashing. But string theory suggests these forces are just different octaves of the same fundamental vibration, all arising from the symmetrical interplay of strings in higher dimensions. It's as if the universe has been playing a chord this whole time, and we're only now learning to hear it. The most tantalizing hint lies in those Calibrated shapes. To understand why, think of a shadow puppet. The same hand can cast silhouettes of a rabbit, a bird, or a wolf, depending on how it's held against the light. Similarly, our three-dimensional universe might be a shadow of these higher dimensional symmetries, with particles appearing distinct only because we're seeing a flattened projection of their true, multidimensional forms. This could explain why electrons and quarks seem so different. They're the same string vibrating in alternate geometries, like a single note echoing differently through a cathedral versus a tunnel. Yet for all its beauty, string theory remains a cathedral in the clouds. Without experimental proof, it's easy to dismiss as mathematical poetry. But consider this: when physicists derived the properties of hypothetical particles from string theory's equations, they found perfect matches for the known particles of the Standard Model, as if the universe had been whispering the answers all along. Even more compelling, the theory naturally includes gravity's quantum counterpart, the graviton, something no other framework achieves so effortlessly. The catch: detecting these higher dimensions or strings directly would require energies trillions of times beyond what our colliders can reach, leaving us to hunt for indirect clues, like subtle gaps in particle behavior or cosmic fingerprints from the early universe. So is string theory a dead end or a roadmap to reality's deepest layer? The answer might lie in the very symmetries it celebrates. Just as Newton's laws seemed complete until Einstein revealed their hidden assumptions, our current physics might be a low-energy approximation of a far grander symmetrical truth. Whether the universe ultimately confirms or refutes string theory, one thing is certain: the quest to uncover its secrets has already reshaped our understanding of symmetry's role, not as a decorative flourish, but as the scaffolding of existence itself. And if history is any guide, whenever we've followed symmetry's trail, it's led us closer to the universe's beating heart. Quantum mechanics doesn't just tolerate symmetry, it dances to its rhythm. At the subatomic level, particles don't behave like tiny billiard balls. They exist as probability waves, their identities spread out like ripples on a pond. Yet even in this fuzzy realm, symmetry is the silent conductor orchestrating every interaction. Take the wave function, the mathematical heartbeat of a quantum particle. It's not a chaotic scribble, it's a finely tuned equation that respects symmetry principles, ensuring an electron orbiting a hydrogen atom in Tokyo behaves identically to one in a distant galaxy. This isn't just consistency, it's the universe enforcing a rule so strict that violating it would unravel physics itself. Then there's entanglement, quantum mechanics' most baffling teamwork act. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. At first glance, this seems to defy locality, the idea that influences can't travel faster than light. But hidden beneath the surface is a deep symmetry. The combined system of both particles remains unchanged under rotations or other transformations. It's as if the universe pre-arranged their fates to preserve a cosmic balance, like two dancers mirroring each other's moves across light years. Albert Einstein called it spooky action at a distance, but that spookiness is just symmetry wearing its most enigmatic mask. Wolfgang Pauli uncovered another symmetry secret with his exclusion principle, the quantum rule that prevents electrons from crowding into the same state. Picture a subway car where every seat is a unique quantum configuration. No two passengers can occupy the same spot with identical properties. This isn't just particle etiquette. It's a direct consequence of antisymmetric wave functions, mathematical expressions that flip their sign when identical particles swap places. Without this symmetry-driven law, electrons would collapse into atomic nuclei, chemistry would vanish and stars couldn't ignite. The stability of matter itself hinges on this invisible quantum handshake. Even the apparent randomness of quantum mechanics, the infamous dice roll at the heart of reality, obeys a subtler symmetry. Probabilities in quantum systems don't scatter wildly. They follow precise statistical patterns rooted in unitary symmetry, a mathematical guarantee that probabilities always add up to 1. It's why Schrödinger's cat isn't just alive or dead, it's both, in carefully balanced proportions until observation breaks the symmetry. This interplay between chance and order might seem paradoxical, but it's the universe's way of balancing creativity with consistency, allowing novelty to emerge within strict boundaries. Quantum fields take this further, their very existence tied to symmetry transformations. The standard model's equations remain unchanged when you tweak them in specific ways, rotate a particle's phase, say, or swap matter for antimatter. These aren't just mathematical quirks, they demand the existence of force-carrying particles like photons and gluons. James Clerk Maxwell's equations hinted at this centuries ago when they revealed that electric and magnetic fields were two sides of the same coin, united by a symmetry now called gauge invariance. Today, we know this principle scales to the entire quantum realm, stitching together the fabric of reality with threads of symmetry. So while quantum mechanics might seem unpredictable, its chaos is meticulously choreographed. From the exclusion principle's rigid order to entanglement's eerie harmony, symmetry isn't just a feature of the quantum world, it's the foundation. And every time we peer deeper into the atom, we're reminded that the universe's love for balance doesn't end at the quantum edge. It begins there. The universe doesn't just happen to have symmetries, it seems to demand them, at least if life is to exist at all. This startling idea, known as the anthropic principle, suggests that the balance we observe in nature isn't accidental. It's necessary. Imagine tweaking just one fundamental symmetry, say, the precise way electromagnetism couples to electrons. Shift it even slightly, and atoms might never bond into molecules. Stars could fail to ignite. The delicate dance of chemistry that builds DNA, proteins, and ultimately brains would collapse into chaos. Our universe doesn't just tolerate symmetry, it depends on it, like a tightrope walker depends on every subtle shift of balance to avoid catastrophe. But here's where it gets even stranger. Symmetry isn't just present, it's fine-tuned to an almost eerie degree. Consider the strong nuclear force, the glue-binding atomic nuclei. If it were even 5% stronger, hydrogen would fuse so rapidly in stars that they'd burn out before life could evolve. Weaker and heavy elements like carbon, the backbone of biology, might never form at all. Similarly, the slight asymmetry between matter and antimatter, which left just enough ordinary matter to build galaxies, feels less like luck and more like a carefully calibrated setting. It's as if the cosmos had a recipe for life, and symmetry was its most crucial ingredient. This fine-tuning raises a dizzying question: why this balance? One possibility is that our universe is just one bubble in an infinite multiverse, where countless other universes flicker into existence with different symmetries, most too chaotic or rigid to spawn observers. We find ourselves in this particular cosmos not because it's special, but because it's the only kind where beings like us could arise to ponder it. It's the ultimate observer bias, like a fish marveling at how perfectly water fits its gills without realizing other environments exist. Yet there's another, more radical interpretation. What if symmetry isn't just a prerequisite for life, but its deeper cause? Think of DNA's double helix, its two strands mirroring each other with near-perfect precision. This symmetry isn't just aesthetically pleasing. It enables replication, error correction, and evolution. Or consider the hexagonal symmetry of snowflakes and honeycombs, shapes that maximize strength while minimizing energy. Life doesn't merely survive within symmetrical frameworks, it exploits them, turning cosmic balance into evolutionary advantage. The anthropic principle doesn't answer whether this fine-tuning implies design, accident, or some deeper law we've yet to uncover. But it does spotlight Symmetry's dual role as both architect and sculptor of reality. The same principles that dictate how quarks interact also shape the structures of living cells, as if the universe were unfolding a single grand pattern across scales. And every time we discover another finely balanced parameter, another symmetry that had to be just so for stars to shine or neurons to fire, we're left wondering, is this the universe's way of telling us that life isn't just possible here, but inevitable? Or is it proof that we're reading the cosmic blueprint backward, mistaking effect for cause? Either way, the message is clear. Symmetry isn't just a feature of our universe, it's the very thing that makes our universe ours. Without it, there'd be no planets to walk on, no atoms to think with, no laws to discover. And that might be the most profound symmetry of all. The way the universe's deepest rules and our ability to understand them seem perfectly, improbably matched. Picture a room full of compass needles, all perfectly aligned, each tiny magnet pointing north in flawless unison. Now turn up the heat. As temperature rises, those orderly needles begin to jitter, their alignment faltering until the room becomes a chaos of spinning magnets. This is symmetry breaking in action, a phase transition where order gives way to something new. The universe itself has undergone similar transformations, moments when its perfect symmetries fractured like ice cracking under pressure, creating the rich diversity we see today. Take the electroweak symmetry breaking, one of the cosmos' most pivotal events. In the universe's first trillionth of a second, the electromagnetic and weak nuclear forces were fused into a single, symmetrical force, like two languages spoken as one. Then, as temperatures dropped below a critical threshold, this unity shattered. The Higgs field, which had been symmetric and invisible, suddenly condensed into a new state, like water vapor freezing into frost. Particles that once zipped through this field unimpeded like electrons and quarks suddenly found themselves slogging through a kind of quantum molasses, acquiring mass in the process. Photons, meanwhile, slipped through untouched, remaining massless. This single transition didn't just break symmetry, it created the very conditions for atoms, chemistry, and ultimately life. Phase transitions like this aren't unique to particle physics. They echo across scales from the mundane to the cosmic. Consider liquid water freezing into ice. At high temperatures, water molecules move freely, their arrangement fluid and symmetrical in every direction. But as temperatures drop, that symmetry breaks. The molecules lock into rigid, hexagonal patterns, creating ice's crystalline structure. The universe's phase transitions follow the same script, just at energies a trillion times more extreme. What's astonishing isn't just that these transitions happen, it's how they sculpt reality. When the strong nuclear force separated from the electroweak force earlier in the universe's history, it didn't just create a new interaction. It allowed quarks to bind into protons and neutrons, the building blocks of atomic nuclei. Without this fracture, stars would lack the fuel to shine. Even the slight asymmetry in how the weak force treats matter and antimatter, a tiny imperfection in the cosmic mirror, might explain why we live in a universe filled with galaxies rather than empty radiation. These moments of symmetry breaking aren't failures of nature's design, they're its creative engine. Like a sculptor chiseling a block of marble, the universe uses these transitions to reveal hidden structures within the formless. The very laws we take for granted, gravity's pull, light speed, the stability of atoms, are the echoes of symmetry-breaking events that occurred before the first stars flickered to life. And as we study these transitions in particle colliders and supercomputer simulations, we're not just reconstructing cosmic history, we're uncovering the grammar of creation itself, the rules that turn simplicity into complexity, uniformity into diversity, and energy into everything. Dark matter doesn't just hide in the shadows, it might be the universe's best-kept symmetry secret. Picture an ancient artifact buried beneath layers of time, its origins lost to history. Dark matter could be something similar, a cosmic relic from an era when the universe was hotter, denser, and more symmetrical than we can imagine. Among the leading candidates is the WIMP, or weakly interacting massive particle, a hypothetical heavyweight that barely notices ordinary matter exists. Its aloofness isn't random, it's a clue. The WIMP reluctance to interact could be the fingerprint of a long-lost symmetry, one that governed particles in the early universe but faded as temperatures dropped, leaving only these ghostly remnants behind. Think of it like a grand ballroom where dancers once moved in perfect sync. As the music slows, some dancers leave, but a few linger, unchanged, still moving to the old rhythm. Dark matter could be those holdouts, particles preserving symmetries that the rest of the universe abandoned. This idea isn't just poetic, it's mathematically precise. Supersymmetry, for instance, predicts that every known particle has a heavier, symmetrical partner. The lightest of these partners, often the neutralino, would be stable, nearly invisible, and exactly the sort of candidate astronomers need to explain why galaxies don't fly apart. Yet dark matter's elusiveness is more than a scientific challenge, it's a cosmic whisper. Its refusal to interact electromagnetically means it doesn't absorb, reflect, or emit light, making it detectable only through gravity's subtle tug. When galaxies spin faster than their visible mass should allow, or when light bends around seemingly empty space, we're seeing the gravitational handiwork of this hidden architect. Some theories suggest dark matter isn't just passively obeying old symmetries, it might be actively enforcing them, stabilizing galaxies like an invisible scaffold. The hunt for dark matter isn't just about filling gaps in our theories, it's about uncovering a deeper layer of reality, one where symmetries we've never seen still shape the cosmos. Experiments like the Large Underground Xenon Detector or the Alpha Magnetic Spectrometer on the International Space Station are essentially listening for echoes of that lost era. Every time a detector fails to find WIMP where we expected them, it's not a setback, it's a refinement, narrowing the possibilities until only the truth remains. And the implications go beyond particle physics. If dark matter is indeed a relic of symmetry, its discovery wouldn't just solve a mystery, it would rewrite our understanding of cosmic evolution. The same symmetries that birthed dark matter might have influenced how galaxies clustered, how black holes formed, even how the first stars ignited. It's as if the universe left us a puzzle where every piece is a different shade of shadow, and solving it could reveal not just what's missing, but why the picture looks this way at all. So when astronomers map the distribution of dark matter using gravitational lensing, or when physicists analyze collisions in underground labs, they're not just chasing a phantom. They're tracing the contours of a symmetry so profound it's woven into the fabric of reality, one that's been hiding in plain sight since the dawn of time. And if history is any guide, every time we followed symmetry's trail, it's led us to truths more astonishing than we dared imagine. Black holes twist the very notion of symmetry into paradox. From the outside, they're cosmic minimalists, their event horizons flawlessly smooth, their gravitational pull indifferent to whether they're swallowing stars or spacecraft. The no-hair theorem, a cornerstone of black hole physics, insists these behemoths can be described by just three features: mass, spin, and charge. Like perfect spheres carved from space-time, they erase all other details, as if the universe hit a cosmic reset button on complexity. This ruthless simplicity isn't just aesthetic, it's symmetry enforced by gravity's ultimate victory over all other forces. But cross the event horizon and the rules shatter. Inside a black hole, space-time curvature becomes infinite at the singularity, a place where Einstein's equations fail and quantum gravity must take the wheel. Here, symmetry doesn't just bend, it may dissolve entirely. The orderly laws governing the external universe could give way to quantum foam, a seething mess of virtual particles and fluctuating dimensions where concepts like before and after lose meaning. It's as if symmetry, having sculpted the cosmos with such precision, finally meets its match in the heart of darkness. The tension between these two regimes, the black hole's serene exterior and its chaotic core, has become physics' greatest testing ground. Stephen Hawking's discovery that black holes slowly evaporate through quantum radiation forced scientists to confront an existential question. When a black hole vanishes, does the information it swallowed disappear forever, violating quantum mechanics' sacred symmetry of information conservation? The holographic principle offers a tantalizing solution, suggesting all 3D events within the black hole might be encoded on its 2D surface like a cosmic DVD. If true, it would mean even in destruction, black holes preserve symmetry, just in ways we're only beginning to decipher. What makes black holes so pivotal isn't just their extremes, but what they reveal about symmetry's limits. They're cosmic laboratories where general relativity's smooth symmetries collide with quantum mechanics' probabilistic rules. Some theorists believe resolving this clash will require new symmetries, perhaps supersymmetry linking particles across dimensions or hidden dualities, making black holes mathematically equivalent to quantum systems without gravity. Others suspect black holes are signposts to a deeper truth. That symmetry isn't fundamental but emergent, like the illusion of a smooth tabletop that's actually made of grain upon grain of wood. Every photon that spirals into a black hole's maw carries with it a piece of the puzzle. As we study their gravitational waves, their shadowy silhouettes against bright gas, even their potential connections to dark matter, we're not just probing collapsed stars. We're mapping the boundary where symmetry, the universe's most reliable architect, either triumphs or surrenders to something stranger. And whatever waits beyond that horizon, it promises to rewrite our understanding of reality's deepest patterns. What if the symmetries we consider fundamental aren't universal truths, but cosmic accidents? The multiverse theory dares to suggest exactly that: a vast ensemble of universes, each with its own unique set of physical laws, where the delicate balances we take for granted might be rare exceptions rather than rules. In some of these universes, electromagnetism could overpower gravity, making stars flicker out too quickly for planets to form. In others, the strong nuclear force might not bind quarks tightly enough, leaving atoms unstable. Our universe, with its precise symmetry breaking that allows for galaxies, chemistry, and life, could be one lucky lottery ticket in a sea of losing combinations. The beauty of this idea lies in its audacity. Instead of asking why our universe's symmetries are so finely tuned for complexity, we might instead ask, what if they only seem fine-tuned because we're here to observe them? This is the essence of the anthropic principle applied to symmetry. Imagine walking into a clothing store where every shirt fits you perfectly. It's not because the store was designed just for you. It's because you're browsing the one rack in a warehouse of ill-fitting options where the sizes happen to match. Similarly, our universe's life-permitting symmetries might not reflect intentional design, but a statistical inevitability across infinite possibilities. String theory adds another layer to this puzzle. If the extra dimensions it proposes are compactified into different shapes across the multiverse, each configuration could yield distinct symmetries and thus different physical laws. A Calabi-Yau manifold with 6 tightly curled dimensions might produce a universe where quarks can't form protons, while another geometry might allow for forces we've never imagined. Some versions could even host entirely new conservation laws where symmetries we consider sacred, like the preservation of energy, don't apply at all. Yet the multiverse isn't just a theoretical playground. It's a lens that reframes how we think about symmetry's role. If our universe's balance is just one variation among countless others, does that make it less profound? Or does it deepen the mystery, suggesting that symmetry isn't a rigid law but a spectrum of possibilities? The answer might lie in the cosmic microwave background, where faint anomalies, slightly uneven patches in the afterglow of the Big Bang could hint at collisions with other universes, each with its own symmetry signature. This perspective doesn't diminish symmetry's importance, it redefines it. Instead of being the universe's immutable foundation, symmetries become dynamic, contingent features shaped by the chaotic birth of cosmic domains. And if that's true, then every snowflake, every spiral galaxy, every quantum entanglement we observe isn't just a product of symmetry. It's a testament to the incredible improbability of our particular corner of existence, where the dice rolled in just the right way for balance to emerge from chaos. Life doesn't just adapt to symmetry, it embodies it. Consider the DNA molecule, its 2 strands spiraling in perfect harmony like dancers locked in an eternal embrace. This double helix isn't just elegant, it's functional. The symmetry allows for precise replication, each strand serving as a template for the other, ensuring genetic information passes flawlessly from one generation to the next. Even the way enzymes proofread and repair DNA leans on this symmetry, correcting errors by comparing one strand to its mirrored partner. It's as if life's blueprint was designed with a built-in fail-safe, a reflection of the same balance that governs galaxies and quantum fields. Now shift your gaze to the starfish, its 5 arms radiating outward like spokes on a wheel. This radial symmetry isn't arbitrary, it's a masterstroke of evolutionary engineering. With no front or back, the starfish can move in any direction equally well, respond to threats from all sides, and even regenerate lost limbs with astonishing precision. Compare that to the bilateral symmetry of a human body or a butterfly, where left and right halves mirror each other. This design streamlines movement, optimizes sensory organ placement, and maximizes efficiency. From the microscopic symmetry of viruses to the branching fractal patterns of trees, biology is a gallery of symmetrical solutions to life's challenges. But why does symmetry dominate life's architecture? One answer lies in physics' unbreakable grip on biology. The same forces that shape snowflakes and galaxies, minimizing energy, maximizing stability, also sculpt living forms. A symmetrical body plan distributes weight evenly, reduces drag in water or air, and simplifies developmental processes. Embryonic cells divide with geometric precision, following chemical gradients as reliable as magnetic fields. Even at the molecular level, proteins fold into symmetrical shapes because asymmetry often means dysfunction. A misfolded protein can spell disease. Yet there's a deeper mystery here. When a sea urchin's spine grows in a Fibonacci spiral or a sunflower's seeds arrange themselves in golden ratio patterns, we're seeing math etched into flesh. These aren't just accidents of evolution, they're echoes of universal constants, as if life is tapping into the same cosmic rulebook that guides planetary orbits and quantum spins. Some scientists speculate that symmetry isn't just a tool life uses, it's a language life speaks, a shared syntax between biology and physics. Of course, nature also thrives on calculated asymmetry. The human heart leans left, lobsters have a dominant claw, and even our brains exhibit lateral specialization. But these exceptions prove the rule. Symmetry is the baseline from which life deviates for strategic advantage. Like a jazz musician riffing on a scale, biology plays with symmetry's themes, bending but rarely breaking them. So when we marvel at a nautilus shell or the hexagonal eyes of a dragonfly, we're not just observing adaptation. We're witnessing a continuum, a thread connecting the quantum to the cosmic, the inorganic to the alive. Whether symmetry arose in life by cosmic inheritance or convergent evolution, one thing is clear: the universe's love for balance didn't stop at the edge of physics. It's written into every cell, every organism, every ecosystem, as if life itself is the universe's way of admiring its own reflection. Art and architecture whisper a truth we've always sensed: symmetry isn't just pleasing, it's profound. The Parthenon's columns, spaced with mathematical precision, or the Taj Mahal's mirrored perfection aren't merely aesthetic choices. They're echoes of a universal language, one that resonates from the spirals of galaxies to the structure of atoms. Even in music, symmetry weaves through Bach's fugues, where melodies fold back on themselves like cosmic origami, creating harmony from repetition and variation. This isn't coincidence, it's a subconscious homage to the patterns that govern reality itself. Our brains seem wired to celebrate symmetry. Studies reveal that across cultures, people consistently rate symmetrical faces as more attractive, a preference so ingrained it appears in infants as young as a few months old. Evolutionary psychologists suggest this bias isn't shallow, it's survival. Symmetry often signals health, genetic fitness, and resilience against environmental stressors. A butterfly's wings matching perfectly or a tree's branches dividing with fractal precision aren't just beautiful, they're indicators of a system functioning as it should. In a world where asymmetry can signal disease or dysfunction, our preference for balance might be nature's way of steering us toward stability. But could this pull toward symmetry run deeper than biology? Ancient civilizations certainly thought so. The mandalas of Hindu and Buddhist traditions, with their concentric circles and geometric precision, weren't just art, they were maps of the cosmos, meditative tools to align human consciousness with universal order. Islamic mosaics, built from intricate tessellations that repeat infinitely, reflect a worldview where mathematics and divinity intertwine. Even Gothic cathedrals, with their soaring vaults and rose windows, encoded sacred geometry into stone, as if the architects sought to crystallize heaven's blueprints on earth. Modern science offers a tantalizing parallel. The same golden ratio that structures seashells and sunflower seeds also appears in the proportions of the Parthenon and Da Vinci's Vitruvian Man. Fractal patterns, which repeat at every scale, govern everything from river networks to Jackson Pollock's paint splatters. When artists unconsciously lean on these patterns, they're tapping into something primordial, a resonance between human creativity and the universe's foundational rhythms. This raises a provocative question. Is our artistic obsession with symmetry a cultural construct, or is it written into our neural wiring by eons of evolution in a symmetrical universe? The answer might be both. Just as the universe balances chaos and order, our love for symmetry bridges instinct and intellect, biology and cosmology. Every time we marvel at a cathedral's arches or lose ourselves in a symphony's recurring themes, we're not just appreciating art, we're glimpsing the invisible scaffolding of existence, a reminder that beauty and truth often share the same geometry. Mathematics doesn't just describe symmetry, it breathes it, thrives on it. At its core, math is a symphony of patterns where every equation, every theorem, is a dance of balanced relationships. Take group theory, the branch of mathematics that studies symmetry in its purest form. It doesn't just catalog shapes that look the same when flipped or rotated. It uncovers the hidden rules governing how symmetries combine, transform, and interact. Imagine a kaleidoscope where each twist creates a new, perfectly symmetrical image. Group theory is the study of how those twists relate to one another, revealing a universe where even the simplest geometric shapes obey profound, universal laws. Then there's the Fibonacci sequence, nature's favorite numbering system. Start with 0 and 1, add them to get the next number, and repeat. Soon, you've got a sequence where each number is the sum of the two before it. Simple, right, but look closer and the magic unfolds. Divide any Fibonacci number by its predecessor, and as the numbers grow, the ratio locks into the golden ratio, approximately 1.618. This same ratio appears in the spirals of sunflower seeds, the curve of hurricanes, even the branching of trees. It's as if nature has a cheat sheet, and mathematics is the language it's written in. Fractals push this idea even further. These infinitely complex shapes repeat their patterns at every scale, whether you zoom in or out. The Mandelbrot set, one of the most famous fractals, isn't just a mesmerizing swirl of colors. It's a mathematical object where every tiny segment, no matter how small, contains echoes of the whole. Coastlines, mountain ranges, even the branching of blood vessels in your lungs follow similar fractal symmetries. The universe seems obsessed with this kind of self-similarity, as if it can't resist repeating its favorite designs across dimensions. But perhaps the most breathtaking fusion of symmetry and math lies in the Langlands program, a sprawling web of conjectures linking number theory to harmonic analysis. At its heart, it suggests that deep symmetries in one area of math mirror those in another, like two sides of a cosmic coin. Prime numbers, those indivisible building blocks of arithmetic, turn out to have hidden symmetries that resonate with vibrations in abstract geometric spaces. It's as if the universe encoded its love for balance not just in shapes and sequences, but in the very fabric of logic itself. This mathematical elegance isn't just beautiful, it's eerily practical. The equations describing quantum mechanics, relativity, and even the behavior of fluids all rely on symmetry principles. When physicists search for new particles or engineers design stable structures, they're leaning on the same mathematical symmetries that govern seashells and galaxies. The more we explore, the clearer it becomes. Symmetry isn't something we impose on the world. It's the world's native tongue, and mathematics is how we've learned to listen. The hunt for symmetry's deepest secrets is accelerating, powered by machines that push the boundaries of what we can observe and calculate. Imagine particle colliders like the upgraded Large Hadron Collider, now capable of smashing protons together at energies once thought impossible. Each collision a microscopic reenactment of the universe's fiery infancy. These experiments aren't just brute force, they're precision instruments tuned to catch whispers of supersymmetry, extra dimensions, or even particles that could rewrite the standard model. Every unexpected bump in the data, every anomaly in detector readings, might be symmetry's signature hiding in the subatomic noise. Meanwhile, floating above Earth's atmosphere, next-generation telescopes like the James Webb and the upcoming Nancy Grace Roman Space Telescope are scanning the cosmos for symmetry's cosmic fingerprints. By mapping the distribution of galaxies with unprecedented clarity or analyzing the polarization of ancient light from the Big Bang, these observatories could reveal whether the universe's large-scale symmetries hold clues to its birth, or if hidden fractures in spacetime's fabric hint at dimensions beyond our perception. Then there's the quantum revolution. Quantum computers, with their ability to simulate systems too complex for classical machines, might soon model symmetrical phenomena we can't yet replicate in labs. Picture a quantum processor untangling the behavior of hypothetical particles in higher dimensional spaces, or testing how symmetries break under conditions mimicking the universe's first moments. These aren't just thought experiments, they're bridges to realities that could exist beyond our current mathematical reach. The stakes couldn't be higher. If supersymmetry is confirmed, it wouldn't just add new particles to the chart. It would expose a hidden layer of cosmic order, a mirror universe of partners to every known particle. If extra dimensions are real, they might explain why gravity seems so feeble compared to other forces, its strength diluted as it leaks into unseen folds of spacetime. Even failures to find these predicted symmetries would be transformative, forcing us to confront whether nature's elegance lies in rules we haven't yet imagined. What makes this era so electrifying is the convergence of tools and ideas. Colliders, telescopes, and quantum computers aren't working in isolation. They're weaving a net to catch symmetry in all its forms, from the quantum foam to the cosmic web. And as we refine these technologies, we're not just testing theories. We're peering into the universe's operating system, searching for the source code that makes reality tick. The answers, when they come, won't just satisfy curiosity. They'll redefine what we know about existence itself and our place within it. Symmetry might not just shape the universe, it could be the hidden architect of consciousness itself. Picture the human brain with its billions of neurons firing in intricate, synchronized patterns. These aren't random sparks. They form networks so precisely balanced that information flows like water through a fractal river, integrating seamlessly across regions. Some neuroscientists suggest that consciousness emerges from this symphonic harmony, where symmetrical connectivity allows disparate thoughts, sensations, and memories to weave into a single, unified experience. It's as if the mind mirrors the cosmos, where symmetry stitches chaos into coherence. Take the thalamus, the brain's central relay station. Its symmetrical connections to the cortex create feedback loops that bind sensory input into perception, much like how gauge symmetry in physics ensures forces behave consistently across space. When these neural symmetries break, as in disorders like schizophrenia or epilepsy, the fabric of consciousness frays, revealing how deeply our inner world depends on balance. Even the brain's default mode network, active when we daydream or reflect, exhibits symmetrical activation, hinting that self-awareness might rely on the same principles that govern star formation or quantum entanglement. This idea ventures into the hard problem of consciousness. Why does subjective experience exist at all? Philosophers like David Chalmers argue that no amount of physical explanation can fully account for the vividness of feeling a sunset or the sting of loss. But if consciousness arises from symmetrical integration, a kind of neural phase transition, where fragmented signals unite into awareness, it might explain how matter gives rise to mind. The universe's love for symmetry could be the missing link, a bridge between the objective laws of physics and the private glow of sentience. Consider the visual cortex, where information from both eyes merges into a single, seamless image. This binocular fusion isn't just a trick of perception. It's a microcosm of how symmetry binds multiplicity into unity. At a deeper level, theories like integrated information propose that consciousness corresponds to the degree of interconnectedness within a system. The more symmetrical and interdependent the parts, the richer the experience. A photodiode senses light, but only a brain, with its symmetrical networks, knows what light means. The implications ripple beyond biology. If consciousness is symmetry in action, could artificial intelligence ever achieve true awareness? Current neural networks, for all their complexity, lack the dynamic symmetries of living brains. But if we engineer systems with similar integrative balance, might we birth a new kind of mind? Conversely, could extraterrestrial life, evolving under different physical constraints, develop consciousness through entirely unfamiliar symmetries? The answers might lie in the universality of mathematical patterns, suggesting that any sufficiently complex symmetrical system, whether carbon-based or silicon, could harbor inner light. This isn't just speculation, it's a frontier. Experiments using transcranial magnetic stimulation to disrupt neural symmetry temporarily alter consciousness, blurring the sense of self. Meanwhile, physicists ponder whether quantum coherence, with its delicate symmetries, plays a role in brain function. Though controversial, the idea underscores a profound possibility that the same symmetries guiding particles and galaxies might also orchestrate thought. Whether these connections hold or unravel, one truth remains: the mind's order and the universe's aren't just parallel. They might be partners in a dance older than time, where symmetry spins chaos into meaning. Time seems to play by different rules depending on where you look. At the microscopic level, the equations governing particles work flawlessly, whether time runs forward or backward, a perfect symmetry baked into quantum mechanics and relativity. Flip the sign on time in Schrödinger's equation, and it still holds. Yet glance at the macroscopic world, and time's arrow feels undeniable. Eggs scramble but never unscramble. Coffee mixes with cream but never separates, and we remember the past but not the future. This paradox, the stark contrast between time's reversible laws and its irreversible experience, is one of physics' greatest puzzles, and its solution might rewrite how we understand symmetry itself. The culprit behind this apparent asymmetry is entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases over time, giving us a statistical explanation for why processes seem to move in one direction. Imagine a deck of cards perfectly ordered by suit and number. Shuffle it once and it becomes disordered. Shuffle it 1,000,000 times and it will never spontaneously return to its original state, not because it's impossible, but because the number of disordered states vastly outweighs the ordered ones. The universe operates similarly, evolving from low entropy order to high entropy disorder, creating the illusion of time's one-way flow. But here's the twist: entropy's rise doesn't explain why the early universe had such staggeringly low entropy to begin with. The Big Bang appears to have been an anomaly, a state of extraordinary order that set the clock ticking. Some theories suggest this initial low entropy wasn't random, but a consequence of deeper symmetries we've yet to uncover. Picture a cosmic hourglass. The Big Bang might represent the narrow waist where symmetry was maximized, and time's arrow emerged as that symmetry fractured, like sand slipping irreversibly to the bottom. The mystery deepens when we consider quantum gravity. In black holes, where space-time curvature becomes infinite, entropy and time behave strangely. The holographic principle suggests that all information within a black hole is encoded on its surface, a symmetrical duality that hints at time's fundamental reversibility. Meanwhile, experiments with entangled particles show quantum correlations that seem to defy classical notions of causality, as if time's arrow blurs at the smallest scales. What if time's asymmetry isn't a flaw but a feature? Just as broken symmetry in the Higgs field gave particles mass, the arrow of time might be a creative fracture, a necessary departure from perfect reversibility that allowed complexity and observers like us to exist. The answer could lie in the quantum origins of space-time, where time emerges from more fundamental, symmetrical building blocks we can't yet perceive. Every tick of the clock, then, isn't just a moment passing. It's an echo of the universe's first and most profound symmetry, breaking the event that made history possible. Quantum entanglement doesn't just challenge our intuition, it shatters it. Imagine two coins flipped on opposite sides of the galaxy, landing with their faces mysteriously linked. If one lands heads, the other instantly shows tails, no matter the distance. This isn't science fiction, it's the eerie reality of entangled particles, a phenomenon Einstein famously dismissed as spooky action at a distance. But beneath the spookiness lies a profound symmetry, one that binds particles in ways that defy space and time. At its core, entanglement is a partnership where the state of one particle is inseparably tied to another, even if they're light years apart. Measure the spin of an entangled electron here on Earth, and its partner on Mars snaps into a complementary state instantaneously, as if the universe forgot to tell them they're supposed to obey the speed limit of light. This isn't a signal traveling between them. It's a fundamental symmetry that transcends distance, a cosmic thread stitching reality together in ways we're only beginning to grasp. What makes this symmetry so radical is how it upends classical physics. In Newton's world, objects interact by bumping into each other or through fields that propagate at finite speeds. But entanglement suggests a deeper layer where particles share a hidden harmony that doesn't rely on proximity or force. It's as if the universe keeps a secret ledger, balancing the books of quantum states faster than any signal could travel. This isn't just weird, it's a clue that the symmetries we see in everyday life might be shadows of something far more interconnected. The mathematics behind entanglement reveals its symmetrical heart. When two particles entangle, their combined state is described by a single, unified wave function, a mathematical entity that treats them as one system, not two separate parts. Rotate or manipulate one particle, and the wave function adjusts globally, preserving the relationship between them. This isn't action at a distance, it's symmetry in its purest form. A reminder that what we perceive as separate entities might be facets of a single, underlying reality. Experiments have tested this symmetry to absurd extremes. Scientists have entangled particles and separated them by over 1,000 kilometers, only to find their correlation holding firm. Others have shown that even delaying the measurement of one particle until its partner has already been observed doesn't break the link, as if the universe retroactively enforces the symmetry, rewriting the rules of cause and effect. These results don't just baffle physicists, they hint that entanglement might be the universe's way of maintaining a cosmic balance sheet, where every quantum transaction is perfectly reconciled. But here's the twist: entanglement doesn't violate relativity, even though it seems to. While the correlation between particles is instantaneous, no useful information can be sent faster than light. It's like having twin light switches in separate galaxies. Flip one, and the other flips too, but you can't control which one does what. This delicate dance preserves causality while flaunting locality, a paradox that keeps theorists awake at night. Some speculate that entanglement reflects a deeper, non-local reality, where space and time are emergent properties of a more fundamental symmetry we've yet to uncover. The implications ripple beyond the lab. If entanglement is a window into a more interconnected universe, it might reshape how we think about everything from black holes to consciousness. The holographic principle, for instance, suggests that the information in a volume of space could be encoded on its boundary, a notion eerily reminiscent of entangled pairs. Even the fabric of spacetime itself might be woven from quantum correlations, with every star and galaxy held together by invisible threads of symmetry. So the next time you hear about entangled particles, don't just marvel at their strangeness. See them for what they are, messengers of a universe far more united than it appears, where symmetry isn't just a property of objects but the very glue of reality. And as we untangle their secrets, we're not just probing quantum mechanics. We're peering into the cosmic code that binds all things, one spooky connection at a time. Consider the fine structure constant, a seemingly random number, approximately 1 over 137, that governs the strength of electromagnetism. Tweak this value even slightly and stars might never fuse carbon, molecules couldn't bond, and the universe would lose the delicate balance that allows chemistry and life to exist. This isn't unique. Dozens of dimensionless constants, from the proton to electron mass ratio to the cosmological constant, are tuned with similar precision. Their values aren't dictated by any known law. They're brute facts of nature, yet their stability hints at a hidden symmetry orchestrating the cosmos from behind the curtain. Take the proton to electron mass ratio, roughly 1,836. If it were much larger, protons would outweigh electrons dramatically, altering atomic stability. Much smaller, and hydrogen atoms would behave unpredictably, disrupting water's life-giving properties. These constants don't just permit complexity, they demand it, like a locksmith filing a key to fit perfectly into the universe's lock. The sheer improbability of their values has led some physicists to wonder, are these numbers frozen echoes of a grander symmetry, remnants of a unified mathematical framework that fractured as the cosmos cooled? One compelling idea is that these constants aren't arbitrary but emergent. Think of ice crystals forming on a pond. Their intricate patterns aren't random. They're the inevitable result of water molecules obeying symmetrical forces as temperatures drop. Similarly, the constants we measure might be the frozen outcomes of deeper symmetries that govern the universe's fiery infancy. String theory toys with this notion, suggesting that the constants could be determined by the geometry of hidden dimensions, like shadows cast by shapes we can't yet see. In this view, the fine structure constant isn't a standalone number but a cosmic byproduct, a relic of higher dimensional harmony. Yet there's a radical alternative, multiverse theory. If countless universes bubble into existence, each with randomly dialed constants, ours simply happens to be the rare one where the numbers lined up for life. No deeper symmetry required, just statistics, but even here, symmetry whispers. The very fact that life-friendly universes can exist within a vast landscape of possibilities suggests an underlying structure, a mathematical playground where certain combinations naturally recur. It's like shuffling a deck of cards endlessly. Eventually, you'll deal a perfect hand, not because the deck was stacked, but because the rules of the game allowed it. The debate cuts to the heart of physics' greatest mystery. Are we living in a universe finely tuned by symmetry's hand, or a cosmic lottery winner surrounded by infinite silent voids? Perhaps the answer lies in the constants themselves. Their stability over billions of years, unchanged from the early universe to today, implies a robustness that feels more like law than accident. When astronomers measure the fine structure constant in distant quasars, they find the same value as on Earth, a consistency that spans time and space with eerie fidelity. This persistence hints at a symmetry so deep it transcends local conditions, a universal rhythm that even the chaos of the Big Bang couldn't disrupt. Whether that rhythm points to a unifying theory or an unfathomable roll of the dice, one thing is clear: these constants aren't just numbers. They're the universe's signature, written in a language of balance we're still learning to read. And every time we measure them, we're not just doing science, we're decoding the hidden patterns that make existence possible. The shape of the universe isn't just a cosmic curiosity, it's a mirror reflecting the deepest symmetries woven into space-time itself. Picture an ant crawling on the surface of a balloon. If the balloon expands, the ant sees every point moving away from every other point, yet from its two-dimensional perspective, it can't perceive the curvature. We're like that ant, but with a universe that could be flat, closed like a sphere, or open like a saddle. Each possibility isn't just about geometry. It's about how symmetry dictates the fate of everything. For decades, astronomers have scrutinized the cosmic microwave background, the afterglow of the Big Bang, for clues. The patterns etched into this ancient light reveal a startling truth. Space appears flat to within a razor-thin margin of error. A flat universe means parallel lines stay parallel forever, and the angles of a triangle add up to exactly 180 degrees. This isn't just mathematical tidiness. It's a signature of perfect large-scale symmetry, where the energy density of the cosmos is precisely balanced between expansion and collapse. But what if the universe were closed, curving back on itself like the surface of a four-dimensional sphere? In that scenario, symmetry would take on a different flavor. Travel far enough in one direction, and you'd eventually return to your starting point, a cosmic echo of the way a snowflake's symmetry brings its patterns full circle. Gravity would eventually halt expansion, pulling all matter back into a fiery, big crunch. An open universe, by contrast, would curve outward like a saddle, its symmetry forever pulling space apart until galaxies vanish over each other's horizons, leaving a cold, dark void. These aren't just abstract thought experiments. The shape of the universe dictates its destiny, and that destiny hinges on symmetries baked into Einstein's equations. A flat universe suggests a delicate equilibrium, where the kinetic energy of expansion perfectly counteracts gravitational attraction. It's as if the cosmos struck a bargain with itself, balancing forces so precisely that structure could emerge without collapsing or tearing apart. The fact that we observe this balance despite the universe's tendency toward chaos hints at symmetries so fundamental they might predate the Big Bang. Yet mysteries linger. Quantum fluctuations in the early universe should have left subtle imprints on spacetime's curvature, like wrinkles in a stretched fabric. The fact that we don't see them, that the universe appears unnaturally smooth, suggests symmetry's handiwork might extend beyond our current understanding. Some theories propose that inflation, the universe's explosive early growth, ironed out these wrinkles by stretching space to near-perfect flatness. Others speculate that hidden dimensions or a multiverse could explain the precision of our cosmic geometry. Ultimately, the shape of the universe isn't just a question of measurement. It's a window into whether symmetry is a local phenomenon or a universal constant, whether the cosmos is a one-off accident or part of a vaster, more symmetrical whole. And as we map the heavens with ever greater precision, we're not just charting space, we're reading the universe's DNA, searching for the symmetries that gave it form and might one day determine its end. Quantum fields aren't just the invisible scaffolding of reality, they're symphonies of symmetry playing out across every inch of spacetime. Picture an endless ocean where each ripple isn't just water, but a dynamic entity humming with potential, capable of condensing into particles or dissolving back into the void. What keeps this chaos from spiraling into randomness? The answer lies in local symmetries, the unsung conductors ensuring every quantum note stays in harmony. These aren't broad, universal balances like the symmetry of a snowflake. They're finer, more intricate rules that must hold at every point in space and time, like 1,000 invisible hands adjusting the universe's dials moment by moment. At the heart of this order are gauge theories, the mathematical frameworks that describe how fields interact without ever dropping the baton of symmetry. Think of them as cosmic traffic laws, dictating how particles can merge, split, or influence one another while preserving an unbreakable set of rules. For instance, the electromagnetic field doesn't just push electrons around arbitrarily. It follows a gauge symmetry called U1, which ensures that whether you measure an electron's phase in Tokyo or on Mars, the underlying physics stays consistent. This isn't just a nicety, it's the reason light behaves predictably across the cosmos, and why your compass needle aligns with Earth's magnetic field instead of spinning wildly. The real magic happens when these symmetries demand the existence of force-carrying particles. In the 1950s, Chen Ning-yong and Robert Mills uncovered a startling truth. Certain gauge symmetries require the universe to have mediators particles like photons or gluons to preserve balance. It's as if the equations were a musical score missing a crucial instrument, and nature had no choice but to invent it. The photon, for example, emerges as the necessary consequence of electromagnetism's symmetry, while the 8 gluons of the strong force arise from the more complex SU3 symmetry governing quarks. These particles aren't just byproducts, they're the glue holding reality together, enforcing symmetry's dictates at every interaction. The Standard Model, that triumphant catalogue of particles and forces, is essentially a mosaic of gauge symmetries. Each force electromagnetism, the strong and weak nuclear forces, corresponds to a specific symmetry group, a mathematical pattern dictating how particles can transform without breaking the cosmic rulebook. Even the Higgs mechanism, which gives particles mass, doesn't obliterate symmetry, it hides it like a magician's sleight of hand. The Higgs field symmetry is still there, woven into the equations, but it's buried beneath the surface, leaving behind the observable world of weighted quarks and sluggish electrons. Remove these symmetries and the universe would unravel like a sweater with a pulled thread. Electrons might ignore photons, quarks could refuse to bind, and the delicate balance allowing atoms to form would collapse. The very coherence of reality hinges on these invisible threads of symmetry, governing everything from the glow of a distant quasar to the neural sparks in your brain. It's a reminder that what we perceive as solid and stable is at its core a dance of fields, and every step, every turn, is choreographed by symmetry's unyielding hand. Gravity is the cosmic underdog, the weakest of nature's fundamental forces by a staggering margin. A simple fridge magnet can defy the gravitational pull of an entire planet, lifting a paperclip against Earth's immense weight. This mismatch isn't just quirky, it's one of physics' deepest enigmas, the hierarchy problem. Why is gravity's grip roughly 10 to the power of 36 times feebler than electromagnetism's? It's like comparing the strength of a single ant to the combined might of every star in the observable universe. The numbers don't just puzzle scientists, they scream that something fundamental is missing from our picture of reality. Enter supersymmetry, or SUSY, a bold proposal that every known particle has a hidden twin. These hypothetical superpartners would balance the quantum scales, cancelling out the extreme disparities between forces. Picture a seesaw with weights on both ends. Without SUSY, gravity's end sits comically high while the other forces press theirs to the ground. But if superpartners exist, they'd add just enough counterweight to level the playing field, revealing a universe where gravity's apparent weakness is just an illusion masking a deeper symmetry. The equations even suggest these particles should have shown up in our most powerful colliders by now, yet they remain frustratingly absent, leaving physicists to wonder, is SUSY hiding in plain sight, or are we chasing a beautiful idea down a blind alley? Extra dimensions offer another tantalizing fix. Imagine gravity as a force that isn't weak, it's just diluted, leaking into unseen spatial folds beyond our three-dimensional perception. In this scenario, gravity's feebleness isn't intrinsic. It's a side effect of its ability to traverse hidden realms. The math behind this idea traces back to the early 20th century, when Theodore Kaluza and Oskar Klein suggested that electromagnetism might arise from gravity operating in a fifth dimension. Modern string theory has revived and expanded this notion, proposing that the universe could harbor up to 7 extra dimensions, curled into shapes so tiny we'd need particle smashers 1 billion times more powerful than today's to detect them. What makes these theories so compelling isn't just their elegance, it's their predictive power. Supersymmetry, for instance, naturally provides a candidate for dark matter in the form of the lightest superpartner, a particle that wouldn't interact with light but would sculpt galaxies through gravity alone. Extra dimensions, meanwhile, could explain why the universe's expansion is accelerating by evoking a hidden landscape of energies permeating the cosmic fabric. Both ideas hint at a reality far more symmetrical than our current models suggest, where forces we perceive as distinct are threads of a single, grand tapestry. Yet the hierarchy problem isn't just a theoretical curiosity, it's a crisis pointing to gaps in our understanding. Quantum mechanics predicts that virtual particles should flood the vacuum of space, contributing to what's called the Higgs field's energy density. These fluctuations ought to make the Higgs boson unbearably heavy, yet it's astonishingly light. This discrepancy, known as the naturalness problem, suggests either a miraculous fine-tuning or, more likely, new physics waiting to be uncovered. SUSY and extra dimensions aren't the only players. Some theorists propose anthropic reasoning, where we simply inhabit one of countless universes where the numbers lined up just right. Others explore Higgs compositeness, imagining the Higgs as a bound state of more fundamental particles, like a proton made of quarks. The stakes couldn't be higher. Solving the hierarchy problem wouldn't just tidy up the standard model, it could unveil a universe where symmetries now hidden govern everything from the quantum foam to the cosmic web. Whether the answer lies in superpartners, curled-up dimensions, or something even stranger, one thing is clear: gravity's weakness isn't a flaw in nature's design. It's a clue, a breadcrumb leading us toward a deeper truth about how the universe balances its forces. And every experiment, from the Large Hadron Collider to gravitational wave observatories, brings us closer to reading that cosmic blueprint in full. Crystals are nature's love letter to symmetry, each one a miniature universe where atoms arrange themselves in flawless, repeating patterns. Take a snowflake, its delicate hexagonal arms branching with mathematical precision, or the cubic perfection of a salt crystal, its sodium and chlorine ions locked in an alternating dance. These aren't just pretty accidents, they're the result of symmetry's invisible hand, dictating how atoms can stack together without chaos creeping in. The rules governing these arrangements are so strict that crystallographers have catalogued every possible atomic configuration into just 230 distinct groups, known as space groups. Each one represents a unique way symmetry can manifest in 3 dimensions, like a cosmic checklist for building order from the atomic soup. But crystals do more than dazzle the eye. They reveal how symmetry bridges the quantum and classical worlds. At the atomic scale, quantum mechanics governs how electrons orbit nuclei, creating clouds of probability that dictate bonding angles and distances. Yet when billions of these atoms come together, their collective behavior crystallizes into macroscopic shapes we can hold in our hands. The symmetry of a crystal's lattice, whether cubic, hexagonal, or tetragonal, isn't just a geometric curiosity. It's a direct consequence of quantum forces finding equilibrium. For instance, the tetrahedral symmetry of a diamond, with each carbon atom bonded to 4 neighbors, emerges from the precise quantum mechanical preferences of electron orbitals. This interplay between symmetry and structure has revolutionized technology. Silicon crystals, with their orderly cubic lattices, form the backbone of modern electronics because their symmetrical arrangement allows electrons to flow predictably. Liquid crystal displays exploit the delicate balance between order and disorder, their molecules twisting in symmetrical patterns to manipulate light. Even superconductors, materials that conduct electricity without resistance, rely on the symmetrical pairing of electrons in a quantum dance that defies classical physics. Perhaps the most profound insight from crystallography is how symmetry can hide in plain sight. X-ray diffraction, the tool that revealed DNA's double helix, works because crystals scatter X-rays in symmetrical patterns that betray their hidden atomic order. When Rosalind Franklin captured photo 51, the telltale cross of dark spots wasn't just an image, it was symmetry's fingerprint, a coded message about the helical symmetry of life's blueprint. So the next time you admire a gemstone's facets or the jagged edge of a broken quartz, remember, you're not just looking at a rock, you're witnessing symmetry's mastery over matter, a harmony so precise it orchestrates the invisible into the tangible, the quantum into the concrete. And as scientists push crystallography further, probing exotic materials like quasicrystals, whose patterns never quite repeat, they're uncovering symmetry's boundless creativity, one atomic arrangement at a time. Life's molecular machinery runs on a curious asymmetry, one so fundamental that without it, biology as we know it might not exist. Take a close look at the building blocks of life, and you'll notice a peculiar pattern. Amino acids, the Lego pieces of proteins, almost exclusively twist to the left, while sugars, the backbone of DNA and RNA, spiral to the right. This preference, called homochirality, is as universal as it is unexplained. It's as if the universe handed life a set of gloves and insisted we only wear the left ones, while reserving the right for another purpose entirely. Chirality, the scientific term for handedness, isn't just a quirk of biochemistry. It's a make-or-break feature. Imagine trying to shake hands with someone wearing a glove on the opposite hand. The mismatch would render the gesture useless. Similarly, enzymes and other biomolecules rely on precise spatial arrangements to function. A right-handed amino acid in a left-handed protein chain is like a misaligned gear in a clock. The mechanism grinds to a halt. This specificity suggests homochirality isn't incidental, it's a prerequisite for life's complexity. But how did this bias emerge? The early Earth was likely awash in equal amounts of both left and right-handed molecules, like a perfectly balanced seesaw. Somewhere along the way, symmetry broke, tipping the scales toward the configurations we see today. One compelling theory points to outer space. Meteorites like the Murchison meteorite, which crashed into Australia in 1969, contain a slight excess of left-handed amino acids. This hints that cosmic processes, perhaps the polarized light of neutron stars or the magnetic fields of interstellar clouds, could have nudged the balance before life even began. Laboratory experiments add weight to this idea. When scientists simulate the conditions of early Earth with energy sources like ultraviolet light or volcanic heat, they often find slight chiral imbalances emerging spontaneously. It's as if the universe has a subtle bias written into its laws, one that favors certain molecular twists over others. Once this imbalance took hold, it could have snowballed through autocatalytic reactions, where molecules of one chirality catalyze their own production while suppressing their mirror images. Like a snowball rolling downhill, a tiny initial preference might have grown into life's universal rulebook. The implications ripple far beyond Earth. If homochirality is a cosmic phenomenon, not just a terrestrial accident, it could mean life elsewhere follows similar blueprints. Search for amino acids on Mars or Europa, and finding a chiral imbalance might be the strongest clue we're not alone. Conversely, discovering life with opposite chirality would rewrite our understanding of biology's origins, suggesting multiple starting points or even a shadow biosphere right under our noses. Yet homochirality isn't just a puzzle for astrobiologists, it's a window into symmetry's creative power. Broken symmetries, from the Higgs field's fracture to the matter-antimatter imbalance, seem to be the universe's favorite tool for building complexity. Life's handedness might be another example, a tiny crack in nature's mirror that allowed structure to emerge from chaos. So the next time you marvel at a spiral seashell or the twist of a vine, remember, you're seeing more than a pretty pattern. You're witnessing an ancient symmetry breaking, the echo of a moment when the universe chose a direction and life followed. Gaze into the depths of a spiral galaxy, and you're witnessing gravity's masterpiece, a swirling vortex of stars, gas, and dust arranged with near-perfect symmetry. These cosmic pinwheels, like our own Milky Way, don't just spin chaotically. Their arms unwind in precise logarithmic spirals, a pattern where each curve maintains the same angle as it expands outward. It's the same mathematical rhythm found in nautilus shells and hurricane formations, as if nature has a favorite blueprint for organizing spinning systems across scales. What's astonishing isn't just their beauty, but how these symmetrical shapes emerge from the apparent chaos of collapsing gas clouds billions of years ago. The secret lies in density waves, ripples of compressed matter that sweep through galactic disks like cosmic traffic jams. As stars and gas encounter these slow-moving waves, they bunch together, igniting new star formation along the spiral arms while leaving trailing gaps of darkness between them. This self-reinforcing cycle creates the illusion of permanent arms, even as individual stars orbit in and out of them like cars merging on a galactic freeway. The symmetry persists because gravity, the ultimate sculptor, treats all matter equally, whether a hydrogen atom or a giant molecular cloud. Everything responds to the same invisible pull. Elliptical galaxies reveal symmetry's versatility. Unlike their spiraling cousins, these smooth, football-shaped giants display radial symmetry, with stars orbiting in every direction like swarms of bees around a hive. Their near-featureless glow comes from billions of ancient stars moving in randomized orbits, their collective gravity averaging out into a harmonious glow. Some, like Messier 87, even shoot symmetrical jets of plasma thousands of light-years into space, powered by supermassive black holes acting as cosmic gyroscopes. Zoom out further, and the universe's love for symmetry becomes even more pronounced. Galaxy clusters, those sprawling metropolises of hundreds of galaxies, often arrange themselves into startlingly regular patterns. The Coma cluster, for instance, shows an almost crystal-like symmetry, with giant elliptical galaxies evenly spaced like nodes in a three-dimensional grid. This isn't accidental, it's the aftermath of a billion-year gravitational dance, where smaller groups merged and settled into configurations that minimize energy, just as soap bubbles coalesce into perfect hexagonal arrays. Yet the cosmos also flaunts symmetry's creative destruction. When galaxies collide, their neat spirals distort into chaotic tidal tails and rings, but given time, gravity always restores balance. The antennae galaxies, locked in a slow-motion merger, will eventually settle into a new symmetrical shape, perhaps a featureless elliptical. Even our Milky Way and Andromeda are destined to become one symmetrical giant in about 4 billion years, their asymmetry merely a fleeting phase in the universe's relentless pursuit of equilibrium. These patterns aren't just celestial eye candy, they're clues to the universe's deepest workings. The fact that galaxies as different as spirals and ellipticals obey the same fundamental symmetries suggests that gravity, dark matter, and cosmic evolution play by universal rules. When astronomers simulate galaxy formation in supercomputers, they can't reproduce realistic structures unless they account for these underlying symmetries. It's as if the cosmos keeps whispering its preferences through every swirling disk and glowing halo, reminding us that chaos is just symmetry waiting to happen. The quantum vacuum isn't silent emptiness, it's a roaring ocean where particles flicker in and out of existence like waves crashing against the fabric of spacetime. This isn't poetic exaggeration, it's quantum field theory's startling revelation. What we call empty space is actually a dynamic arena where symmetrical fields tremble with potential, birthing particle-antiparticle pairs that annihilate almost instantly. These vacuum fluctuations aren't random chaos, they're bound by strict symmetry rules that dictate which particles can appear, how long they linger, and how they interact. It's as if the universe keeps a perfect ledger, balancing every fleeting electron with a positron, every quark with its antiquark, ensuring the books always zero out. Consider the Casimir effect, where two metal plates placed nanometers apart in a vacuum feel an invisible force pushing them together. This happens because the plates restrict the types of quantum fluctuations that can exist between them, creating an imbalance with the unconstrained fluctuations outside. The symmetry of the vacuum isn't just mathematical, it's measurable, with real-world consequences that nanoengineers must account for when designing microscopic devices. This phenomenon reveals the vacuum's hidden structure, a sea of possibilities where symmetries act like invisible traffic cops, directing the flow of virtual particles. At an even deeper level, the Higgs field permeates this quantum vacuum like an invisible syrup, its symmetrical nature giving particles mass when they interact with it. Before the Higgs mechanism kicks in, particles like electrons and quarks would zip through space at light speed, unable to form atoms or molecules. The moment the Higgs field's symmetry broke in the early universe, like a pencil standing on its tip finally choosing a direction to fall, it created the mass spectrum that makes our material world possible. Yet the field itself remains symmetrical beneath the surface, its underlying order untouched even as its effects shape reality. These quantum symmetries aren't fragile, they're resilient, rebounding instantly when disturbed. When physicists probe the vacuum with powerful particle colliders, they're essentially poking this symmetrical foam to see how it responds. The fact that the same rules govern these extreme conditions as the quiet vacuum of deep space suggests symmetry isn't situational, it's foundational, woven into the universe's operating system at the most fundamental level. Even in the bizarre realm of quantum tunneling, where particles seemingly teleport through barriers, symmetry principles like energy conservation hold firm, proving that the vacuum's chaos is meticulously regulated. What makes this quantum symphony even more astonishing is how it scales. The same symmetrical fields that permit virtual particles to dance in empty space also govern the fusion reactions in stars and the neural firings in our brains. From the infinitesimal to the cosmic, symmetry isn't just a feature of the vacuum. It's the reason the vacuum can give rise to anything at all. And as we peer deeper into this quantum froth, we're not just studying particles, we're deciphering the rulebook that allows existence to emerge from nothingness, one symmetrical fluctuation at a time. If symmetry is truly woven into the fabric of reality, from the spin of electrons to the spiral of galaxies, could it also be the key to unlocking one of humanity's oldest questions? Are we alone? Scientists scanning the cosmos for extraterrestrial intelligence don't just listen for random noise. They hunt for patterns, for signals that stand out against the cosmic background like a perfectly spaced drumbeat in a chaotic symphony. Symmetry, it turns out, might be the universe's most reliable calling card. Consider the famous WOW signal, a 72-second burst of radio waves detected in 1977 that bore the hallmarks of artificial origin. What made it intriguing wasn't just its intensity, it was its narrow frequency range, a precise, symmetrical spike unlike the broadband static of natural astrophysical processes. SETI researchers have since prioritized similar narrowband signals, reasoning that symmetry in frequency could betray the handiwork of technology, but the search doesn't stop there. Imagine an alien civilization engineering a beacon that pulses in Fibonacci sequences or transmits prime numbers, mathematical universals that transcend language or biology. These wouldn't just be messages, they'd be symmetries etched into time itself, a cosmic handshake built on shared principles any intelligent species might recognize. The same logic applies to megastructures. If advanced civilizations build Dyson spheres or orbital rings to harness stellar energy, these constructs might cast symmetrical shadows on their host stars, regular dips in light curves that repeat with clockwork precision. Astronomers already use this principle to spot exoplanets. The next anomaly might reveal something far stranger. Even the arrangement of hypothetical alien cities or solar arrays, if visible, could betray geometric patterns reflecting universal efficiencies. After all, symmetry isn't just aesthetically pleasing, it's practical. Hexagonal solar panels, radial transit networks, or tetrahedral habitats might emerge independently across the cosmos as optimal solutions to energy, transport, or structural challenges. Yet the most tantalizing clue might lie in biochemistry. On Earth, life's preference for left-handed amino acids and right-handed sugars suggests that homochirality isn't just a fluke, it could be a universal constraint. If alien microbes or complex organisms share this bias, their atmospheres might contain telltale imbalances in chiral molecules, detectable by next-generation telescopes like the James Webb. Symmetry, in this case, wouldn't just be a signal, it'd be a fingerprint, a chemical signature written in the same language of molecular geometry that governs life here. This raises a profound possibility. If symmetry truly underlies the universe's laws, then the principles guiding our search for extraterrestrial intelligence might not be human inventions at all. They could be cosmic imperatives woven into the fabric of physics and chemistry, waiting to be discovered by anyone or anything that learns to look. The symmetrical patterns we cherish in snowflakes, galaxies, and quantum fields might be more than beautiful accidents. They could be the universe's quiet instructions for how to build a civilization, or at least how to find one. And as we peer deeper into the void, we're not just scanning the darkness for signs of company, we're testing whether symmetry is the thread that binds all thinking minds together. From the quantum flutter of particles to the grand whirl of galaxies, symmetry reveals itself as the universe's most persistent whisper, a hidden language written into the fabric of reality itself. Every snowflake's intricate design, every atom's predictable behavior, even the way galaxies spiral in perfect mathematical harmony, they all point to a cosmos that doesn't just tolerate order, but thrives on it. This isn't coincidence, it's cosmology's greatest clue. The forces that bind nuclei, the fields that give particles mass, the very shape of space-time, all obey symmetrical laws so precise they can be distilled into elegant equations. But here's the breathtaking implication. Symmetry isn't merely a property of the universe. It might be the reason the universe exists at all. Think of symmetry as nature's ultimate multi-tool. In the subatomic realm, it dictates how particles interact, ensuring electrons orbit nuclei with flawless precision. On Earth, it shapes the hexagonal perfection of honeycombs and the spiral growth of ferns, solutions perfected by evolution because they minimize waste and maximize efficiency. And in the depths of space, it molds galaxies into sweeping arms and clusters into vast, repeating patterns, as if gravity itself is an artist working from a symmetrical blueprint. These aren't disconnected phenomena, they're threads of the same cosmic tapestry, woven together by laws that favor balance. What's truly remarkable is how symmetry bridges the abstract and the tangible. The same mathematical principles that describe the spin of an electron also predict the existence of black holes. The Higgs boson, discovered after decades of searching, was found not by accident, but because symmetry demanded it. Even the mysterious dark matter that holds galaxies together might be a relic of symmetries that governed the universe's fiery infancy. Time and again, when physicists have followed symmetry's trail, it's led them to truths more profound than they imagined. Yet symmetry isn't rigid, it's dynamic, creative. The universe doesn't just preserve symmetry, it breaks it, and in doing so, generates diversity. The slight excess of matter over antimatter, the chiral twist of DNA, even the arrow of time, these asymmetries aren't flaws. They're the universe's way of turning simplicity into complexity, energy into life. Without these fractures, stars wouldn't shine, molecules wouldn't bond, and consciousness couldn't emerge to ponder the very symmetries that made it possible. So the next time you marvel at a butterfly's wings or lose yourself in the fractal branches of a tree, remember, you're not just seeing beauty, you're glimpsing the universe's operating system, a code of balance that transcends scale and substance. And as we continue to decode this cosmic cipher through particle colliders, space telescopes, and quantum experiments, we're not just studying the universe. We're learning its grammar, one symmetrical revelation at a time. If this journey through the hidden patterns of reality has sparked your curiosity, let us know in the comments, and join us next time as we dive deeper into the mysteries that shape existence. Until then, keep looking closer. The universe's secrets are often hiding in plain sight.